with an apology. I, of course, don't mean literally all complete intersection Calabi-Yau fourfolds. There's a bad habit which I've fallen into this little part of the literature where people refer to complete intersections in products of projective spaces as CCs, or just complete intersection Calabi-Yaus. So a much more modest set than the title would suggest, I'm afraid. So this is work I've done with Alexander Haupt, who's in Hanover, and Andre Lucas, who's in Oxford. And there's an initial small paper on the archive, and there's a bigger one coming up, and I'll tell you what's going to be in each. And the basic idea is to give a set of matrices that, in some sense, classify all Calabi-Yau fourfolds that can be described as a complete intersection in the product of projective spaces. And it's important to mention that this is essentially follow-on work to some much earlier, much earlier work by Candelas and his collaborators on classifying Calabi-Yau threefolds in a similar way. They came up with a set of 7,890 matrices that classify all complete intersection Calabi-Yau threefolds in products of projective spaces right back in the 1980s. And this is the same thing for fourfolds. So one thing you could ask is, why didn't these guys do the fourfolds back in the 1980s? And there's two essential reasons. One is that the algorithm that they used in this setup doesn't trivially extend to the fourfolds. The number 3 is used in explicit ways. But I don't think that would have been any impediment to these guys to actually carry on and make the fourfold list. The real problem is that the fourfold list is absolutely huge compared to the threefold list, and computer power back in the day just wasn't enough to get the job done. So they had to be really clever even to get the threefold list to work, let alone the fourfold. And so this is just a project that's time has come. You know, the computers are now fast enough. We have interest in fourfolds, so we now do it. So,
this is working.
What do I do? Kind of intermittent. It's all right, I'll just wave my hands, that's fine. Thank you. Okay. So what is it we're actually going to classify? We're actually going to classify matrices, and they're just configuration matrices that describe families of Calabi-Yaus. So here's an example. I know lots of people in the audience are familiar with this, but just to get us all on the same page, what you do is you describe your Calabi-Yau as some intersection of hypersurfaces inside a project of projective spaces. Here it's P1, P2, P3. And then you have a series of columns of integers that describe the polynomial equations that give you that algebraic variety. So here we have one that's bilinear in the coordinates of P1 and P2, and another one that's linear, quadratic, and quartic in the ambient space coordinates. And of course, each of these matrices describes an entire family of Calabi-Yaus. If you write down these polynomials, say the first one, it's a bilinear, but there's some coefficients in the polynomials you write down. And those coefficients, if you like, are a redundant description of part of complex structure moduli space. So you just have this family of Calabi-Yau as you're describing by this, this matrix. And the reason that you want to describe them this way is because that's essentially a matrix of integers, and computers like that. Right? So more generally, we're going to have a first column of integers, m of them, will just describe our m projective ambient spaces. And then we have next to that an m by k matrix. So we have k defining relations in our m spaces. And so we just have a complete matrix of integers that's going to describe each of these families of Calabi-Yau manifolds. So a couple of initial basic properties is that if you want the complete intersection to be 4-dimensional, then the complete dimension of the number of ambient space minus the number of equations better be 4. And if you want this to be Calabi-Yau, it's rather easy to show using a junction that the sum of the integers here in this row has to be equal to the dimension of the projective space plus 1. And that makes sure that the first Chern class vanishes, and we've got a Calabi-Yau. OK, so if you want to classify such things, you may immediately see a problem, which is that I can just keep making this matrix bigger and bigger and bigger and still get Calabi-Yaus, right? So I can keep adding projective ambient space factors, and as long as I add enough equations, I'll still get a fourfold. And so this data set, as I've just described it, is obviously unbounded. The crucial point is that different matrices can describe the same sets of configurations. So there's redundant descriptions of the Calabi-Yaus, redundant matrices. We just need to figure out enough of the redundancies to bring the set into being something finite, and then we can turn on the computer. So how do we do that? Well, to make the set of matrices finite, we just need to bound the dimension of the ambient space. That's also going to bound the number of equations, so it will bound both m and k, the dimensions of the matrices. And I'm just going to, this is one of those things that you can show rather nicely in a short period of time. So at least for how you bound part of this problem, I'm actually going to take you through it. So the bounds for the fourfold case, which are very similar to the threefold case, are that if you look at the number of P1 factors in your ambient space, which is S, you can't have more than, well, if you can get an irredundant description of all of the Calabi-Yaus by restricting the number of P1s to be 12 or less. And if you look at the number of Pn factors with n greater than or equal to 2, which I'm calling P, there has to be less than 8 of those. And furthermore, the total dimension in the Pn's with n greater than or equal to 2 is also bounded. So if I define alpha to be a sum over the dimension minus 1 over all of the Pn factors with n greater than or equal to 2, that alpha has to be less than 8. So that looks like a pretty weird object to define, but we'll see why it's useful in a sec. Thanks, man. Go away. Fine. OK. So how do we show the finiteness of this? How do we show these bounds, and therefore this class of matrices that we need to consider is finite? Well, I'm just going to show you the first of these two. So I'm just going to show you how to get the first one here. This one is given by something very similar. It's just fiddly to do, so I'm not going to take you through it. OK, so how do we do this? Well, for the fourfold to be a complete intersection, we need k, the number of equations, to be equal to the total dimension of the ambient space. That's the number of P1s plus the total dimension in other Pn factors minus 4. If you look at how I defined alpha here as this sum of n minus 1, you can just rearrange this as s plus alpha plus p minus 4. OK, very simple. You can also ask what the total degree of the equations are. So sum the total degree of all the equations, sum all of the integer entries in your matrix. Well, you know by the Calabi-Yau condition that each row has to sum to the dimension of that ambient space plus 1. So for each P1 factor, we're going to get a 2. For each Pn factor with n greater than or equal to 2, we get n plus 1. And again, if you use the definition of alpha and you sum that all up, you get 2s plus alpha plus 2p. OK, so far we've just written down some numbers. We haven't introduced an identity that's going to allow us to make this data set finite. So that's what we do now. So the identity is not that complicated. We're just going to use the fact that a linear in Pn just defines Pn minus 1. Okay. So the basic idea, observation you use using this fact is this. Imagine that you have a configuration matrix, some big matrix, and one column is just a series of zeros, or 1, and then more zeros. What you could do in such a case is you could delete that column, and then in the row where you had that 1, so zeros here, and then this 1, you can just replace this Pn with a Pn minus 1. So you shrink the number of columns by 1, you replace this Pn, and you get a new configuration matrix, which is the same thing, or describes the same set of Calabi-Yaus. Why does that help you with finiteness? Well, what that tells you is that for any column in the matrix, if you sum it, you'll get at least 2. Because the only other option you've just removed. Given that, if you know that the smallest column sum that you can get is 2, you know that the sum over all columns, the total degree, has to be at least 2 times the number of columns, right? So you know that d is greater than or equal to 2k. So now if you just plug in k and d as we have them, you find that you get this expression. The s's and the p's cancel out, and you get the A alpha, this sum basically telling you about the total possible dimension in the Pn's, has to be less than or equal to 8. So that's this first bound. The P is less than alpha follows trivially from this definition. So it really is very, very simple manipulations that allow you to show that you can make this class finite. For this bound, for the bound on the number of P1s, you do something similar, and the identity that you have to use turns out to be this one. But you just do similar manipulations, and you can show that this class is finite. So given that you only have to consider a finite number of matrices, what you could do is just literally try and dumbly make all of them on a computer, and just try and write down every configuration matrix that obeys the rules of the right dimension and being Calabi-Yau using these bounds. That's a bad idea because the resulting list will be still hugely redundant and just too big to deal with. Nevertheless, it works for the ambient spaces. There's 660 of them, and this is a list of them in some notation. So you have P1 to some number, P2 to some number, and then P4 squared, for example. Just get a list of possible ambient spaces. So that you can do by brute force, but you can't list all of the matrices themselves this way because there's too many. So you need a more efficient algorithm, and that's what I'm going to go through now. So the algorithm has two parts, one of which is to do things a stupid way for a subset, and then you go on and look at how you're going to get the rest of the Calabi-Yaus after that. So first of all, we're going to focus on complete intersections that we can describe in products of projective spaces that involve no p1s, so only pn with n greater than or equal to 2. The thing you gain by doing that is instead of having to consider all 660 ambient spaces that are possible, you find that only 62 are necessary, and then we really can essentially brute force things. So you can write down all integer matrices that obey the rules. You have to be a little bit careful because, of course, for example, if you permute rows, all you're doing is relabeling your projective space factors, and that's going to give you a massive increase in the number of matrices you consider for no extra information. Similarly, if you permute columns, you're just relabeling your defining equations and gaining nothing. So how you generate things, you have to be a little bit careful, but especially in the fourfold case, but I'm just going to ignore all that. Once you've removed that kind of trivial redundancy and just brute forced out all the Calabi-Yaus with only Pn factors, you get 9,522 different matrices. Now, one thing we want to do is, as far as we can, is we want to make this list of matrices minimal, in that we don't want too many matrices describing the same set of Calabi-Yau manifolds, if at all possible. So at each step of this algorithm, we're going to do a trimming where we just get rid of the chaff. We get rid of anything that's already described. And I'm just going to describe how we do that in general at this step, and then we'll repeat it when we do other steps. So when we have a set of matrices, there's a number of matrices that we just delete or replace with new matrices using identities, and I'm just going to take you through what we do. So first of all, if you have something that looks, for example, of this form, you have I don't know, a couple of points in P1 times a Calabi-Yau, you just want to keep the Calabi-Yau, right? This is not a useful thing to have. So anything that's this product of Calabi-Yau zerofolds, if you like, times a Calabi-Yau fourfold, we delete and just keep the fourfold. Of course, this wouldn't be present in the Pn list, but it's present later on. We do keep products of things like a Calabi-Yau threefold times T2. That's for checking purposes, and we'll see it later. There's a whole series of identities that we reduce, the set with respect to. When they did the Calabi-Yau threefold list, they had more identities that we used than just these. Not all of those had been rigorously proved, but they needed to do it to get the list down to a manageable size. We're just using the ones that have been rigorously proved, just simply because computers are faster now and we don't need basically to take the chance. It turns out that they were right anyway, and when you actually compute the Calabi-Yau threefold list just using these identities, you get the same thing. So another set of identities, and all of these take one matrix, like the top one where you have two sets of columns, a P2 and a Pn, and gives you a smaller matrix. So for example, it replaces this P2 with a P1 and a slightly different configuration matrix. So that's two sets of different identities that we use to remove redundant descriptions. Another one, which is slightly more complicated, is called contraction, or going the other way, splitting. So it's contraction going this way, splitting going this way. So if you just have a Pn and a row of ones, and then some zeros at the end of that column, and then the rest of the matrix is arbitrary, this type of Calabi-Yau can, under certain conditions, be the same as this one. So what are the conditions? Well, so first of all, in nomenclature, if these are the same, we call this an ineffective split or an ineffective contraction. And if they're different Calabi-Yau, we call it an effective split or an effective contraction. And it's very easy to, if you stare at an example, to see what's going on. So this is a split of the bicubic. So if I look at this thing, it's defined by two equations. And if I label the P1 factor here, it's homogeneous coordinates by Z0 and Z1, I can write these two equations in matrix format. So these are, I guess, degree 1, 2 polynomials in P2, P2, and these are degree 2, 1. So these are the defining equations of this Calabi-Yau, but because you obviously can't have both homogeneous coordinates on P1 being 0, this equation has a solution if and only if the determinant of this matrix vanishes. The determinant of that matrix is a degree 3, 3 polynomial, 1, 2 plus 2, 1. So it's a special example of a bicubic inside P2, P2. So if you like, these two matrices describe a set of configurations that share a point in moduli space. And the question then becomes, is that point singular or not? If this is smooth, then you can smoothly move from one Calabi-Yau to the other, and so we're going to count them as one. But if not, then you've got a problem.
One's a block.
Yeah, that's exactly right. So for example, when is this singular? This is singular when this matrix has rank 2 less than maximal. Then what you'll get here in a threefold case is points, and then this is P1 blow-ups of those points. Yeah, that's right. But if there are no singular points here, so in this case, these are different Calabi-Yaus. But if there are no singular points, you can just smoothly sort of move between one and the other, I guess. In fact, this is the threefold case, where you will always find for any PN split that the singular points that you get are literally point-like. And that means you can tell whether this is an effective split or not just by working out the difference in the Euler number between these two matrices. One of the complications that comes in the fourfold case, which I'm not going to go into, is that because everything's one-dimensional higher, the singular locus is one-dimensional, if it exists at all, which means that it could be a torus, which means that the Euler number can stay the same between the two configurations, and yet they're different. You can't smoothly move from one Calabi-Yau to the other. So what you have to do is you can't just calculate Euler number on either side to decide whether a split is effective. You have to come up with some procedure for how you're going to decide whether you can smoothly go from one Calabi-Yau to the other. We do that. Basically, you slice everything with hyperplanes to get it down to being point-like again. There's a description of this in the paper. So far, in terms of identities, I've almost finished with them. We get rid of this kind of thing, get rid of those. Get rid of contractions if they're ineffective, and then also row and column permutations, as I said. OK. So, yeah, sorry.
Quick question. So the example of the effective splitting is where you change the row number of threefolds.
Yeah.
Just confolds.
Yeah.
And it's known to the original data set of 8,000 that everything in that data set is connected by 3 such.
I know what you're going to ask, yeah.
Is it known for, I mean, you were talking about starting with some minimal set and then moving outwards. Is it known that these conifolds will cover everything?
My memory isn't crisp, but I think so. I think there's a paper by Ilka Brunner and her collaborators where they show that everything goes to 2, 2, 2, 2, 2 in a column. But I can check for you. I'm not 100% sure. OK. So we're going to back to the algorithm. So we're going to generate everything that's only got PNs in the ambient space. We then apply these identities to trim things down. When we do that, some of those identities will introduce P1s. So we now have some P1 factors in the ambient space, but we definitely don't have all possibilities. In fact, there are no matrices that would be of the form P1, 1, 1, and then a bunch of zeros, for example. So one of the things that Philip Gandelis and his collaborators showed when they first did the threefolds is that you could generate the rest of them just by doing successive P1 splittings of this type. And because we know how many P1 factors we can have in total, up to 12, that's a finite number of P1 splittings you have to do. In fact, the bounds are rather weak, both in the threefold and in the fourfold case. In the fourfold case, you only have to do 11 splittings before you get everything. So what you do is you generate the PN-only list, you reduce identities, you do a split to get the first of the P1 splittings, you do reduce with identities, split, identities, split, identities, and eventually you can show you get the entire list. So what do you get? So in the threefold case, you got 7,890 matrices, eventually. In the fourfold case, you get just under 1 million, I guess. Of course, if you can't check this in any sensible by hand way, so you want to have some confidence that the code is right. So first of all, you check that you get the same list for the threefolds, which you do. And this is also where we left the products in. So for example, you could have Calabi-Yau fourfolds that are product of any of the Calabi-Yau threefolds on a torus. You could have 4 tori. You could have 2 tori and a K3. And you can work out, if you got your algorithm implementation right, exactly how many of those cases they should be and what they should each be. And then you just compare. So 15,813 of these guys are not interesting in that way, but we get them right, so we've got some confidence that the code is working. Just to emphasize again that some redundancies are still present, and I'm not sure how we would ever be confident of removing all possible redundancies in this list. So if a mathematician has some ideas would be interested. One thing that you can do for sure, of course, is you can just work out topological invariance and differentiate things that are different, at least that way. The obvious one to try first is the Euler number, Euler characteristic, but that's not too differentiating. In fact, there's only 206 different Euler characteristics in the list. Don't worry, there's a lot more Calabi-Yau fourfolds than that. You can expect the number of Calabi-Yau fourfolds to be of the same order of magnitude as the number of configuration matrices. That's the case in the threefold cases, and we're seeing hints of that in what we're doing for the second paper now. But nevertheless, caution is needed. The data, so the complete set of matrices, together with the code that created it is available on the archive submission, and also in the abstract of the paper, there's a link to a web page where you can just download a Mathematica file with it all in a Mathematica list. So if you want to do something with the set, it's all there. And if we can help you with any of it, if there's any particular data about the Calabi-Yau you want, if we can do it, we'll give it to you.
Can you compute Betty numbers?
I'm going to talk about that in a minute. Yeah. So what else can we compute? So one thing we would, for the type of application we've eventually got in mind, is elliptic vibration structure. In general, finding all possible elliptic vibrations of one of these guys, I don't know how to do it. Again, interested if anyone's got any ideas. But there's a subset that we can just spot. So imagine that I can rearrange my matrix so it has this format with a block of 4 matrices inside, split the ambient space into 2 pieces, and a naught here. And furthermore, I'm going to arrange the dimensions such that this is a Calabi-Yau one-fold, just a torus. Then the claim is that this is an elliptic vibration over this base. So heuristically, the way to see this is, imagine picking any point on this manifold. So pick homogeneous coordinates in this ambient space that satisfy these equations. Then what I will have here is the homogeneous coordinates that satisfy these equations will go into these polynomials to fix these coefficients of the A1 homogeneous coordinates in these polynomials. And so for each point on this base manifold, you'll get one description of T2. And as you move around the manifold, that description will change as the factors in the polynomials here get modified. So in other words, this is the base, this is the fiber, and this describes how the fiber is twisted over the base. So, yeah.
Everything in this family is fiber, or just some special example?
Really good question. So, in fact, it's down here. So, because these matrices are rather large and kind of sparse, most of them are. So, of these 900,000, all but 400.
If I think of a set of matrices, one set of matrices gives me a family of Calabi-Yau 4 folds.
Yes.
Is everything in that family elliptic family, or just some special ones?
Everything in that family, because this zero structure, which is where it's coming from, does not depend on the polynomial prefactors. You're quite right. If I then allowed myself to go to special examples, then I might pick up extra vibrations.
K3s, for example, only special ones. And that's not in this.
I would just completely miss them because I couldn't pick it up.
The result of Collar, which actually says that under very mild assumptions, if any member of the family is vibration.
So dimension 3, that's classic collaborative extended with dimension 4.
Ah, that's interesting. So you're saying if I don't see one in this set, there is nothing? Or?
No. One member of the moduli space, one elliptic vibration, the elliptic vibration to 4, at least in the generic point.
Yeah, so this would describe the generic point. So, yeah.
Not only that, he has a numerical criterion which works for elliptic vibrations which are not isotrivial.
Okay. So the point was we wanted to have a class that we had a hold on, and seeing as many of these matrices have hundreds of these different elliptic vibrations that when you do all this redundancy removal we're doing look to be different, you know, there's hundreds times 900,000 different elliptic vibrations here. So at least for us that was going to be enough. If there's some chance that we can get everything, we'd be very interested to know. Okay, so there was questions about what else we can do. So we have code to compute Hodge data that we've used for many other projects, for example, with Lara, and of course it's not quite good enough to resolve all the Hodge data. So we've got 3,700 different sets of Hodge numbers so far for this set of Calabi-Yau, but we weren't able to compute everything. So we need this for many different projects. So we're writing new code based on Bott-Braille-Weiland spectral sequences that will compute all the Hodge data. So that will be ready in a few months, and that was what will be in the big paper. So we'll give you all of the Hodge data. The Chern classes for this set are easy to compute. For anything that descends, I'm almost finished, thanks. For anything that descends from the ambient space, so for any hyperplanes that descend from the ambient space, working out the intersection numbers is easy, so that we can do as well. We'll combine all the different topological invariants in different ways to get as good a bound as we can on how many of these manifolds are different. That bound obviously will be a lot more stringent than what we currently have. And we'll give a classification of this elliptic vibration structure, but as I defined it earlier, if there's something better we can do, that would be awesome. And then we'll move on to applications. But if there's anything anybody else wants that can just be got from this set of matrices, then we're willing to give it a go to get it out. Okay, that's all I wanted to say. Thank you.
Questions?
also look at complete intersections in toric varieties with this kind of technology, or?
You could. That data set will be absolutely vast. So the threefold guys didn't look at the fourfolds because the data set was too big. So I'm kind of hesitant because someone then comes along and actually does it. But my guess would be that you can't cope with that. I mean, even fivefolds in projective spaces, I suspect the data set is too large to deal with.
Right, one last question. Do you know what the largest, so fourfolds constructed systematically in toric varieties use a single hypersurface and some complete intersections?
Weighted spaces, there's some stuff by
there's,
Schimmer.
there's some, it's on the order of a few 100,000 examples. Do you know
Yeah.
what the biggest data set besides this one is?
I think it's the ones by Schimmer in weighted projective spaces, but I could well be wrong. I don't remember. Yeah. So, yeah. The one I'm most familiar with Schimmer stuff because obviously it's kind of closely related and we can do some cross-checks across, but I don't know.
Do you expect your data set is kind of representative, or will it have some kind of bias?
Well, if you look at the threefolds, it's a good example, right? So, when they wrote some initial books on the subject, they thought it is representative, but then they contain no mirror pairs. So if you draw the threefold diagram, they're all on this side. I would guess that there's some special structure coming from this construction. In particular, that's often sort of sorted out by going and looking at the toric hypersurfaces as well, but it's nothing more than a guess. I wouldn't see why such a simple construction necessarily has to give you something generic. But yeah. The advantage of them is that we can do so much with them. So for the type of thing I do, I'm a string phenomenologist, so if we want to calculate very explicit numbers for particle spectra or something, this is the type of manifold that we really can deal with. But, yeah.
No further questions. Let's thank James.